Hello everyone, and welcome back to your online video lecture. In this video, we will be focusing on water and why it's so crucial and beneficial to life. We'll touch on the 4 emergent properties of water, solutions and concentrations, and we'll finish off with acid-base chemistry. For this chapter's objectives, students will model and categorize the fundamentals of molecular structure and functions associated with living organisms. In particular, students will describe molecular polarity and ionization as an influence on molecular interactions and fundamental organization in solutions and cells. And students will model and relate molecular ionization related to acids, bases, and pH. To understand the significance of water, we need to go back 4.4 billion years. Researchers oscillate between water originating on Earth, with the hydrogen inside our planet playing a role in the formation of the oceans, and the idea that water was delivered to Earth by impacts from icy objects from space. Our Earth was formed 4.54 billion years ago, and the origin of water is murky at best. What is clear is that water became a prominent component of the biosphere shortly after the birth of our Earth, and that there was an almost instantaneous emergence of life. The hydrothermal vents in the deepest depths of the ocean is where the story of life begins. These deep-sea vents harbored the conditions conducive to the emergence of primordial life forms that gave rise to all life on Earth. It's no wonder we have an entire chapter dedicated to water. Water not only makes life possible on Earth, it created life on Earth. As oceans were the birthplace of life, water's properties are quite suitable to the continuation and support of living organisms. Water exists in 3 phases on Earth: solid, liquid, and gas. In fact, water is the only common substance to exist in the natural environment in all 3 of these physical states of matter. Here is a phase diagram of water. Along the y-axis is pressure, and along the x-axis is temperature. We see the freezing point at 1 atmosphere, which is where we are at. We see the freezing point at 1 atmosphere of pressure highlighted at 0 degrees Celsius, and the boiling point is shown at 100 degrees Celsius. Water's unique emergent properties arise from the structure of the water molecule, which determines how it interacts with other molecules. In the last lecture, we learned about the various types of bonds: polar covalent, non-polar covalent, hydrogen, and van der Waals forces. Check out my video if you need a refresher. When introducing the polar covalent bond, we discussed water as a great example. Within the water molecule, the electrons of the polar covalent bonds spend more time near the oxygen than the hydrogen. This is due to the unique electronegativities of these atoms. Electronegativity is an atom's affinity for electrons. The larger the electronegativity number, the more that atom will hog the electrons being shared within the bond. Oxygen is highly electronegative, while hydrogen has a low electronegativity. This large difference in electronegativity causes electrons to gather around the oxygen, creating partial charges, denoted by the lowercase Greek letter delta. Remember, electrons have a negative charge while protons have a positive charge. The electronegative oxygen carries a partial negative charge due to the accumulation of electrons, while the hydrogen carries a partial positive charge. Because the 2 OH bonds are polar covalent in nature, the water molecule is a polar molecule in which the overall charge is unevenly distributed, with the electrons favoring the oxygen atom. This polarity of the water molecule results in a new type of bond called a hydrogen bond. Hydrogen bonds are a weak type of intermolecular bond in which the partially charged hydrogen atom of one polar molecule is attracted to the partially negative atom, usually oxygen or nitrogen, of another molecule. Water is special because of this polarity and the resulting hydrogen bonds. The hydrogen bonds are like an intermolecular glue that attracts the water molecules and holds them together. This property of water leads to the occurrence of 4 special emergent properties which contribute to Earth's suitability for life. They are cohesive behavior, the ability to moderate temperature, expansion upon freezing, and versatility as a solvent. The first emergent property is cohesion and adhesion of water molecules. We just learned about those hydrogen bonds that act like a glue between the water molecules. Collectively, this results in a phenomenon called cohesion. You may have witnessed cohesion when you overpour a glass of water and liquid seems to dome above the surface of the glass. This is due to something called surface tension, which is the measure of how difficult it is to break the surface of a liquid. Water has an unusually high surface tension due to hydrogen bonding between the molecules at the air-water surface and to the water below. Again, this is all due to those hydrogen bonds. Surface tension is also the reason why small insects may walk on water. Cohesion also helps to transport water molecules against gravity in plants. Have you ever wondered how water taken in at a tree's roots gets all the way up to the top of a tall tree? In this example, we see the water being taken up by the root via a process called osmosis. We'll learn more about this in a later chapter. The water molecules within the tree's xylem are in contact with each other and thus are forming hydrogen bonds. At the top of the tree, the leaves are losing water due to high temperatures through evaporation. This is called transpiration, which is actually good for the tree because it helps it to cool down. The loss of water molecules at the top creates a difference in hydrostatic pressure, and the water molecules will want to move up the tree to replace the ones that were just lost. This creates another negative hydrostatic pressure down at the roots, which allows for more water to be absorbed. The hydrogen bonds between all the water molecules act as a chain, holding them together so that when water molecules at the top want to rise, they will pull up at the molecule below them. However, this process also involves something called adhesion. Adhesion is an attraction between different substances, for example, between water and plant cell walls. In this case, the adhesion is occurring between the water molecules and the bark of the tree's inner xylem. So note that cohesion is between 2 water molecules, while adhesion is between 2 different substances. So it could be a water molecule and something else. Emergent property number 2 is the moderation of temperature. For this one, we need to revisit our oceans. Did you know that oceans absorb 90% of all heat that humans are adding into the atmosphere? In fact, 2019 was the hottest year recorded for our world's oceans. John Abram, an engineering professor specializing in thermal sciences at the University of St. Thomas, stated, "It's about 5 Hiroshima bombs of heat every second, day and night, 365 days a year." Environmental scientists warn of the dangers of the warming oceans as this accelerates the melting of ice shelves, affecting marine mammal migration patterns, fishery stocks, and coral reefs, and contributes to more intense storm systems. Seawater has high density and can hold 4 times more heat than air. For example, 1 degree Celsius change in the ocean's temperature would be equivalent to a 1,000 degrees Celsius change in our atmosphere. Because of this, Ocean warming is a more accurate way to measure how hot the world is getting than air temperature. Air temperature might be hot one year and cooler the next, but water is denser than air and takes longer to heat and cool. Now you might be wondering how the oceans absorb all of that heat without evaporating. Well, of course there is a cycle of evaporation and rainfall. However, water can absorb or release a large amount of heat with only a slight change in its own temperature. And can you guess what gives water this unique quality? Of course, the answer is hydrogen bonds. The hydrogen bonds formed between the water molecules are able to absorb some of that heat. Because of this, water absorbs heat from warmer air and releases stored heat to cooler air. You may have witnessed this on a cool morning off a lake. The lake absorbs the heat beating down from the sun all day. Then in the morning, when the temperature has dropped, heat is released back into the air and you can see it coming off the lake. This is the moderation of temperature. But what even is temperature? What do we mean when we say heat? We need to cover the second major type of energy to answer this question. Energy occurs in many forms, including chemical energy, thermal energy, electromagnetic radiation, gravitational energy, electric energy, elastic energy, nuclear energy, and rest energy. These can be categorized into two main classes, potential and kinetic energy. In the last chapter, we covered potential energy, which is the energy due to location or structure. Kinetic energy is the energy of motion. As an example, this archer has fully drawn the bow back and is holding it at this position, which has a high potential energy. Now the archer may release the arrow, which will convert that potential energy into kinetic energy as the tension from the bow launches the arrow through the air. When talking about chemistry, the kinetic energy associated with random motion of atoms or molecules has its own name called thermal energy. Probably heard of this word before. It simply describes molecules and atoms in motion. We use the word temperature to describe this thermal energy. Temperature represents the average kinetic energy of the molecules in a body of matter. When thermal energy is transferred from one body of matter to another, we define it as heat. Nearly 66% of the chemical energy that we ingest from food is actually lost as heat, which is why you can feel warmth emanating from yourself and other living organisms. And speaking of chemical energy and heat, what is a calorie? We use calories as our measure of energy in the food we eat, but do you know what it actually means? A calorie, which is lowercase kcal, is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So let's get a visual for this. This black spoon is filled with 1 gram of water. Remember, gram is a measure of mass. 1 gram of water is equivalent to the volume 1 centimeter cube, or we say 1 cubic centimeter, which is also equivalent to 1 milliliter of water. Cubic centimeter and milliliter are both ways to express a volume. So grams is a mass, while the other two are a volume. So 1 calorie is the amount of energy required to raise this gram of water by 1 degree Celsius. It's also the amount of heat released when 1 gram of water cools by 1 degree Celsius. Now that was calories with the lowercase c. The capital C calories that we see on food packages are actually kilocalories, which is kcal. Looking at our table of units, we see that kilo is 1,000 times greater than the base unit. So a kilocalorie is 1,000 lowercase c calories. The joule, represented by a capital J, is another unit of energy. 1 joule equals 0.239 lowercase c calories, or 1 calorie equals 4.184 joules. You'll see joules used more in chemistry and physics class. Related to calories is the property of specific heat. The specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. This sounds a lot like the definition of a calorie, right? Furthermore, the specific heat of water is 1 calorie. So why is the specific heat of water the definition of 1 calorie? You have to remember that all of these units in science that we use to measure things are man-made. They're created as a means to help scientists quantify scientific phenomena. Scientists need to identify a standard which we can use to quantify everything else. And water is often that standard. This is also why 1 gram of water equals 1 cubic centimeter and 1 milliliter. This is not true of all substances. Let's look at the specific heat of another substance, ethanol. Ethanol is alcohol that you would find in beer or wine. Ethanol's specific heat is 0.59 calories. This is much lower of a specific heat than water. This means it takes less energy or calories to heat ethanol. If you've ever used wine or beer in a cooking recipe, you've seen this in real life. The alcohol cooks off and evaporates much faster than water. Water resists changing its temperature because of its high specific heat. And water's high specific heat can be traced to hydrogen bonding. And this is because of the ability for hydrogen bonds to absorb and release energy. Heat is absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. Another way to say this is to break bonds, we need to add heat to them. All of the water molecules in the ocean are held together by a net of hydrogen bonds, which absorb the heat radiating down from the sun. They will only break when they've absorbed enough heat, at which point that water molecule will evaporate away, having absorbed enough thermal energy to transform from liquid to gas. In this way, the high specific heat of water minimizes temperature fluctuations to within limits that permit life. And this is related to evaporation. Evaporation, or also referred to as vaporization, is transformation of a substance from liquid to gas. Now, of course, there are thousands of different liquids that exist, and each will require a different amount of heat to turn it into a gas. We call this the heat of vaporization. Specifically, heat of vaporization is the heat a liquid must absorb for 1 gram to be converted to gas. Just like with specific heat and calories, we are using 1 gram as our mass measure. As I mentioned, scientists like to standardize measuring units. Our bodies utilize the heat of vaporization of water for a process called evaporative cooling. We all know sweating is the primary means of thermoregulation for humans, a mechanism we've adapted to cool us down. But how does it work? Well, that sweat sits atop of your skin where it begins to absorb heat from your body. This heat is converted to thermal energy. Eventually, those water molecules gain enough energy and reach their heat of vaporization, at which time they will convert from a liquid to a gas. As that liquid evaporates, taking away the heat and energy from your body, the surface that it leaves will cool down. This process is called evaporative cooling. In this way, evaporative cooling of water helps stabilize temperatures in organisms and bodies of water. We perspire, and if you recall, trees have their own version of this called transpiration. The third emergent property of water is the floating of ice on liquid water. A quick trip back to elementary school science, and you might remember that buoyancy, or floating, has to do with density. Let's shine a light on density. The density of a substance is the mass per unit of volume. In other words, D equals m over v. Let's use these two sponges as an example. Both sponges have the same mass of 100 grams. However, the bottom sponge has been squeezed to create a smaller volume. The top has a volume of 100 cubic centimeters, while the bottom has a volume 1/10 of that, to just 10 cubic centimeters. Now we can calculate the densities, and they are 1 gram per centimeter cubed and 10 grams per centimeter cubed. The top sponge has a lower density than the bottom sponge because that mass is spread out over a greater volume. Ice floats in liquid water because hydrogen bonds in ice are more ordered, which forces them to spread out, making ice less dense than liquid water. In this image, you can see the ice molecules have formed a crystal lattice structure, and they are highly organized and have no motion, so there's no kinetic energy here. In comparison, the image on the right shows liquid water, whose molecules contain thermal energy, so they are in motion. These molecules are also much closer together than the ice molecules. The crystal lattice structure in ice is able to form because there is a lack of thermal energy, no heat, so no motion. So these bonds are more stable. The liquid water bonds, on the other hand, have more thermal energy and motion, so these molecules are continuously forming and breaking those hydrogen bonds. Ice floats because freezing causes expansion and an increased volume, and this lowers the density. When we heat ice and it melts, the volume decreases, which increases the density. And let's just think about this for a minute. What would happen if ice didn't float? What would happen if it sank? Well, if ice continuously sank, leaving liquid water at the top of a water source, there would be a cycle of freezing and sinking until the entire body of water was frozen. This would kill all life. Because ice floats, an entire ecosystem of wildlife is able to flourish under the frozen lakes and oceans, like this krill here. And not just that, have you ever seen the thermohaline circulation system? Imagine if this global conveyor belt of water, which drives our temperatures and weather patterns, was blocked by a chunk of frozen waters due to ice sinking. If ice sank, all bodies of water would eventually freeze solid, making life impossible on Earth. The fourth and final emergent property of water is water's ability to act as a solvent of life. Let's shine the light on a few important terms before we continue. When we talk about mixtures, we mean a thing that contains two or more substances in any given ratio. The mixtures are then classified by their homogeneity, and we can have completely mixed, partially mixed, or not mixed at all. We have either homogeneous or homogeneous mixtures, or heterogeneous mixtures. A completely homogeneous mixture is called a solution, and this means that their components cannot be distinguished by the naked eye. Heterogeneous mixtures, on the other hand, can be distinguished, and their mixtures include colloids and suspensions, among other things. In a mixture, the solvent is the dissolving agent of a solution. The solute is the substance that is being dissolved. So just remember, the solvent dissolves the solute. An aqueous solution is a special type of solution in which water is the solvent. If you've ever been told to gargle salt water after losing a tooth, in adding salt to water, you've created an aqueous solution. Water is the solvent and salt is the solute. Remember, water is a polar molecule due to the polar covalent bonds, and this makes water very versatile as a solvent. Here's another term for you: like dissolves like. Essentially, water being a polar solvent will easily dissolve any polar atoms or molecules. This includes anything with a charge. When an ionic compound like the sodium chloride shown here is dissolved in water, each ion is surrounded by a sphere of water molecules called a hydration shell. Notice how the partially positive hydrogen of the water molecule is interacting with the negatively charged chlorine ion, while the partially negatively charged oxygen of the water molecule is interacting with the positively charged sodium ion. In this image, we see that water can also dissolve compounds made of non-ionic polar molecules. The purple entity is a protein, which is made of amino acids. We'll get to amino acids in a later chapter, but for now, just note that they can carry a negative or positive charge on them. This allows them to be dissolved by water in a solution. And this makes sense, right? What is the majority of your intracellular fluid and blood made of? Water. We are 71% water. Our proteins need to be able to dissolve in our body. Remember, like dissolves like. Even large polar molecules, such as proteins, can dissolve in water if they have ionic and polar regions. This brings us to a very important concept in cellular physiology, which is hydrophilic and hydrophobic substances. It's very simple. A hydrophilic substance is one that has an affinity for water. A hydrophobic substance is one that does not have an affinity for water. And let's break down those words. Hydro comes from the Greek hydra, meaning water, and philos, meaning loving. It literally means water loving. Hydrophobic also comes from the Greek word hydro for water and the Greek phobos, meaning fearing. So hydrophobic means water fearing. Hydrophilic molecules, the water loving substances, are anything that is polar or charged. On the other hand, hydrophobic molecules tend to be nonpolar, such as oil molecules, which have relatively nonpolar bonds. We'll learn more about this in Chapter 5 when we discuss the macromolecules. Let's do a quick recap. Water is the molecule that supports all life. There are 4 emergent properties of water which lend to its benefits. 1. Adhesion and cohesion are an attraction between water and another substance or water and itself. Cohesion also results in surface tension, which allows insects to walk on water. 2. Moderation of temperature. Water can absorb a large amount of heat with only slight changes in temperature. This is due to water's high specific heat, which is the number of calories needed to raise 1 gram of a substance by 1 degree Celsius. Water has a specific heat of 1. The specific heat of a substance also leads to its heat of vaporization, the heat a liquid must absorb for 1 gram to be converted to a gas. Our bodies use this in sweat and evaporative cooling. 3. Floating of ice on liquid water, which is due to the lower density of ice. If ice sank, all bodies of water would eventually freeze. And 4. Water is the solvent of life. It is highly soluble due to its polarity. Like dissolves like, so water will dissolve hydrophilic substances, substances with polar or ionic regions. Water will not dissolve hydrophobic substances. The chemical characteristic of water that lends to these 4 emergent properties is the polarity of water, which is a result of the polar covalent bonds and leads to special bonds called hydrogen bonds. Now would be a good time for a quick break. The remainder of this lecture is going to focus on calculating different types of solute concentrations and acid-base chemistry. Alright, so this is a biology lecture, but we do still need to cover some chemistry. Biology is chemistry brought to life, and we would be nothing without the trillions of chemical reactions taking place as part of our metabolism. As I mentioned, we are mostly water, so most of our chemical reactions involve solutes dissolved in water, which makes us one giant aqueous solution. There are 3 ways that we can calculate solute concentrations, but before we do, let's shine the light on a few terms. We are going to use mass to calculate the number of solute molecules in an aqueous solution. Remember, molecules are tiny. There's no way that we could actually count the individual molecules of a solution if we were working in a lab. But by using something called the molecular mass, we can quantify the solute and accomplish this. Molecular mass is the sum of all masses of all the atoms in a molecule. Makes sense, right? Molecular mass. We learned about Daltons in the last chapter as the unit to represent mass of an atom because a gram is just too large. Well, there's a little bit more to this. Numbers of molecules are actually usually measured in moles, where 1 mole, which is MOL, equals 6.02 times 10 to the 23rd molecules. This is called Avogadro's number and is a huge number. Think of a mole the way you think of a dozen. A dozen is always 12, and a mole is always 6.02 times 10 to the 23rd. I can have a mole of sodium atoms, I can have a mole of glucose molecules, I can have a mole of students, and this does relate back to Daltons. Avogadro's number and the unit Dalton were defined such that 6.02 times 10 to the 23rd Daltons equals 1 gram. In other words, 1 mole of Daltons equals 1 gram. The mole was defined in such a way that the molar mass of a compound in grams per mole is numerically equal, for all practical purposes, to the average mass of 1 molecule in Daltons. Thus, for example, the average molecular mass of water is about 18.0153 Daltons, and the molar mass of water is about 18.0153 grams per mole. I know this can get a little confusing. When you look at the periodic table, the number you see represents both the atomic mass in Daltons and the molar mass in grams per mole. So to calculate the molecular mass of a molecule, let's use salt, NaCl, as an example. Looking at the periodic table, I see that the atomic mass of sodium, Na, is 23, and chlorine is 35 Cl. NaCl, the compound, contains 1 sodium and 1 chlorine, so I add these two molar masses together to calculate the molecular mass of 58 grams per mole. So if I have 1 mole, 6.02 times 10 to the 23rd molecules of salt, I would have a mass of 58 grams. Let's do one more. Glucose. Glucose is C6H12O6. Looking at the periodic table, I see the molar mass of carbon is 12.01, the molar mass of hydrogen is 1.01, and the molar mass of oxygen is 16. This is a larger molecule. There are 6 carbons, 12 hydrogens, and 6 oxygens. So we need to multiply the molar mass by the number of atoms for each element. So you can see in this table, 6 carbons times 12 grams per mole, because each carbon has a mass of 12 grams per mole. 6 times 12 equals 72 grams per mole. 12 hydrogens times 1 gram per mole equals 12 grams per mole. And 6 oxygens times 16 grams per mole is 96 grams per mole. Sum these numbers to reach a total molecular mass of 180 grams per mole for glucose. So 1 mole of glucose, that's 6.02 times 10 to the 23rd molecules of glucose, has a mass of 180 grams. We need to understand how to calculate the molecular mass in order to understand the first method of calculating solute concentration, which is molarity. Molarity, which is represented by that capital M, is the number of moles of solute per liter of solution. To illustrate molarity, let's walk through a problem. If you dissolve 174 grams of NaCl in 1 liter of water, what will be the concentration of that salt solution in molarity? With word problems, always begin with writing down what you know and calling out what you need to know. What we know is that the solute is salt, NaCl, and we have 174 grams of it. For our solution volume, we have 1 liter of water. The problem is asking for the concentration of this salt solution in molarity, capital M, so I also want to write out the formula for molarity, capital M equals moles over liter. I'll also write the molar mass equals grams per mole. Okay, so we need to figure out capital M, molarity. This means we need to figure out how many moles of salt we have and how many liters of solution. Well, we actually already know this one. We have 1 liter of water, so I will fill this in. We don't have to do any other calculating for this. But we do have to convert that 174 grams of salt into moles. So how can we accomplish this? Luckily, we also wrote down that the molar mass is in grams per mole. We have grams, total grams, but how many moles of salt is this? For this, we have to visit the periodic table and fetch the molar masses for sodium and chlorine. Na, sodium's mass, is 23 grams per mole, while Cl, chlorine's mass, is 35 grams per mole. We already calculated the molecular mass for sodium chloride before. It's 23 plus 35, which gives us a total of 58 grams per mole. So, 1 mole of sodium chloride has a molecular mass of 58 grams. How many moles does 174 grams equate to? For this, just set up a quick stoichiometry problem. Remember with these that the units always have to cross out. So we have 174 grams. We're going to multiply this by a fraction. We're going to use the molar mass grams per mole, but because those grams have to cross out, we're going to do 1 mole over 58 grams. And see, now grams can be crossed out. 174 divided by 58 equals 3, and the unit we have left over is mole. We have 3 moles of sodium chloride. So plug this into the molarity equation. 3 moles divided by 1 liter is a 3 molar solution. Try to figure out this on your own. How many grams of salt do you need to use to make 2 liters of a 1.5 molar salt solution? I'll put the answer at the end of the video. There are 2 other ways to measure solution concentration. We have the percent solution and the mass to volume ratio. In a percent solution, it is always in grams of solute per milliliters of solvent times 100. So for example, what is the percent solution if you have 3 grams of salt in a 150 milliliter amount of water? 3 grams of salt divided by 150 mils times 100 equals 2. So this is a 2% salt solution. And finally, in the mass to volume ratio, this uses any mass of solute and divided by any volume of solvent. For example, if you have a solution of 3,000 milligrams in 1,000 milliliters of water, 3,000 milligrams divided by 1,000 milliliters will give you a mass to volume ratio of 3 mgs per mil, or 3 milligrams per milliliter. And always remember your units. Here are a few more practice problems for percent solutions and mass to volume ratio. Pause the video and give them a try. All of what we've learned so far in this chapter leads us to acid-base chemistry. We all have experiences with acids and bases in our daily lives. For example, we use them daily for cooking and cleaning. Our bodies also strategically use acids and bases for metabolism and homeostasis. Acidic and basic conditions are a crucial aspect of an organism's biochemistry and environment. So let's define them. As a heads up, there are actually a number of ways to define an acid and a base. We are going to use the A Bronsted-Lowry acid is a substance that increases the H+ concentration of a solution, while a Bronsted-Lowry base is a substance that reduces the H+ concentration of a solution. Let's revisit hydrogen for a moment. Recall that hydrogen is a proton in the nucleus with one orbiting electron. Again, an acid is a substance that increases the H+ concentration of a solution. And H+ is a positively charged hydrogen, which means a proton without the electron. For this reason, acids are also called proton donors. And conversely, if a base is a substance that reduces the H+ concentration of a solution, bases are proton acceptors. So, do you think water is an acid or a base? This is a bit of a trick question. A hydrogen atom in a hydrogen bond between two molecules of water can shift from one to the other. When this happens, the hydrogen atom leaves its electron behind and is transferred as a proton or hydrogen ion H+. The molecule that lost the proton is now a hydroxide ion, which is OH-. It has a negative charge because it has one more electron than protons now. The molecule with the extra proton is now a hydronium ion, H3O+, though it is often represented as that H+ ion. So when we say H+, we're actually referring to H3O+. So, is water an acid or a base? It's actually both. It is both a proton donor and proton acceptor. Water is in a state of dynamic equilibrium in which water molecules dissociate at the same rate at which they are being reformed. For this reason, concentrations of H+ and OH- are equal in pure water. When talking about acids and bases, we can have strong acids or weak acids. This just means how easily they dissociate or break apart and release that proton. Strong acids dissociate completely in water. Weak acids reversibly release and accept back hydrogen ions but can still shift the balance of H+ and OH- away from neutrality. Another way of defining acid-base chemistry is with the Arrhenius system. An Arrhenius acid is a substance that dissociates in water to form hydrogen ions or protons, while an Arrhenius base is a substance that dissociates in water to form hydroxide ions, OH-. Adding certain acids and bases to a solution modifies the concentration of H+ and OH-. More H+ corresponds to higher acidity, while more OH- corresponds to lower acidity and higher basicity. We use the pH scale to describe whether a solution is acidic or basic. So let's crunch some numbers. If we have any aqueous solution at 25 degrees Celsius, which by the way, that's room temperature, the product of H+ and OH- is constant and can be written as the concentration of H+ times the concentration of OH- equals 10 to the negative 14. For this annotation, brackets in chemistry and biochemistry mean concentration. So we'd say the concentration of H+ times the concentration of OH-. And you would immediately say 10 to the 14 what? There are no units here. Well, these concentrations are a molarity, capital M, so it should say 10 to the negative 14 molar. So let's just say my solution contains solely water, nothing else. If the concentration of H+ and the concentration of OH- are equal in water, as we said before, what are the respective concentrations? In pure water, H+ equals 10 to the negative 7 and OH- equals 10 to the negative 7. When we multiply exponents, we add those exponent numbers. So 7 plus 7 equals 14. Now that was for pure water. All other solutions will have other H+ and OH concentrations, though they will still all have a constant product when you multiply them of 10 to the negative 14 molar. So that is the concentration of ions in solutions. How do we translate this in an easy-to-read pH scale? We use this formula. The pH of a solution is defined by the negative logarithm of the concentration of hydrogen ions, written as pH equals negative log concentration of H+. So, for a neutral aqueous solution of pure water, we've already determined that the H+ concentration is 10 to the negative 7 molar. So, the pH equals the opposite of the log of 10 to the negative 7, which equals 7. So, the pH of water is 7. You do need a calculator that is capable of performing logarithms for these things, but there is a trick, and we'll get to that in a second. The pH scale runs from 0 to 14. Acidic solutions have pH values less than 7, while basic solutions have pH values greater than 7. Most biological fluids have pH values in the range of 6 to 8. Human blood, for example, falls around a pH of 7.4. We see right in the middle at pH 7 is our neutral friend, water. And notice how the concentration of hydrogen ions is equal to the concentration of hydroxide ions, OH-. Now you'll also notice here that the concentration of H+ is greater than the concentration of OH- for acidic solutions. And for bases, it's reversed. The concentration of H+ ions is lower than the concentration of OH- ions. Remember this formula. Concentration of hydrogen ions times the concentration of hydroxide ions equals 10 to the negative 14. Here we see a representation of hydrogen ions in comparison to hydroxide ions in a solution. Notice at neutral pH 7, the concentrations are the same. At the low pH ranges to the left, we see higher concentrations of H+ and gradually lower concentrations of OH-. The opposite is true if we move to the right. The hydrogen ion concentration drops, it plummets, while the OH- rises. We can see that the H+ concentrations along the top and the OH concentrations along the bottom. 10 to the 0 is actually 1. So the top left shows the highest concentration of H+ for acids at 1 molar. If you need a quick refresher on exponents, every time we see 10 with an exponent in front of it, there is actually a 1. So it is 1 times, and then your exponent, 10 to the negative 1. 1 times 10 to the negative 13. When you see a negative number, this is telling you to move the decimal to the left. And if you see a positive number after that exponent, it's telling you to move it to the right. So for 10 to the negative 1, which is 1 times 10 to the negative 1, we move the decimal to the left 1 space, which gives us 0.1. For 10 to the negative 10, which is 1 times 10 to the negative 10, we move the decimal to the left 10 times. So don't let the large number next to the 10 fool you. The larger the negative exponent, the smaller that number becomes. So back to our formula. The concentration of hydrogen ions times the concentration of hydroxide ions equals 10 to the negative 14. We can see this is true using the table that I drew up here. The rows we have are pH, concentration of hydrogen ions, concentration of hydroxide ions, and pOH. If pH equals negative log of the concentration of hydrogen ions, pOH equals the negative log of the concentration of hydroxide ions. But it's really quite simple. Look at pH 11 for the full column filled in. If a solution has a pH of 11, the concentration of hydrogen ions is 10 to the negative 11. You just take that pH and you set that as the negative exponent. We want the exponents to add up to 14, right? 10 to the negative 14 divided by 10 to the negative 11, you would do 14 minus 11, which is 3. So the concentration of hydroxide ions is 10 to the negative 3. If the concentration of hydroxide ions is 10 to the negative 3, then the pOH is 3. And look at pH plus pOH, that equals 14. Always. Make a chart like this and fill them in. It's really good practice, and it's an easy way to understand acids and bases without having to understand logarithms and all the math that goes on beneath it. And one final thing, this pH scale is called a logarithmic scale. Specifically, it's using a logarithm to the base of 10. This means between each pH value, so if we take a pH of 0 and a pH of 1, there's actually a difference of 10-fold, or 10 times the concentration. The difference between pH 0 and pH 2 is 10 times 10. So this is actually a 100-fold difference, or 100 times difference in concentration, with the pH of 0 having a 100 times greater concentration of hydrogen ions than the pH of 2. For a little bit of practice, what is the pH of a solution containing 1 times 10 to the negative 5th molar of hydrogen ion? What is the pH of a solution containing 1 times 10 to the negative 8 molar hydroxyl ion? And what is the fold difference in hydrogen ion concentration between solution A, which has a pH of 4, and solution B, which has a pH of 9? The last thing we need to discuss is buffers. The internal pH of most living cells is close to 7, and it's vital that they remain that way. Buffers are just substances that have the ability to minimize change in concentrations of H plus and OH minus in a solution. Most buffer solutions contain a weak acid and its corresponding base, which combine reversibly with hydrogen ions. In the example we see here, carbonic acid, which is H2CO3, is a type of weak acid formed from the dissolving of carbon dioxide in water. Bicarbonate, which is HCO3, is the deprotonated form of carbonic acid. Bicarbonate serves a crucial biochemical role in our pH buffering system by helping to maintain a healthy physiological pH. It works by either accepting a proton to become carbonic acid or donating a proton to become carbonate. So that's it for our water chapter. We covered a lot. We covered the emergent properties of water, we talked about solutions, and we even got into a little bit of acid-base chemistry. In the next chapter, we will be diving into carbon and the crucial role that it plays in building biological molecules for us.